Weather forecasting, presented by Connor Ellis, Dan Isaac, and Robert Gatos. Weather forecasting has been around for a very long time. In 650 BC, the Babylonians tried to predict short-term weather changes based on the appearance of clouds and optical phenomena such as halos. In 300 BC, Chinese astronomers had developed a calendar that divided the year into 24 festivals, each festival associated with a different type of weather. In 340 BC, Aristotle wrote Meteorologica, a treatise that included theories about the formation of rain, clouds, hail, wind, thunder, lightning, and hurricanes. Aristotle made some remarkably accurate observations concerning weather, along with some significant errors. His 4-volume text was considered by many to be the authority on weather theory for almost 2,000 years. The hydrometer was invented in the mid-15th century as an instrument used to measure humidity. Galileo invented an early thermometer in 1952. Torricelli invented the barometer for measuring atmospheric pressure in 1643. The invention of the telegraph in the mid-19th century allowed for the transmission of weather forecasts and the formation of the first early weather maps to show wind patterns. Predicting the weather by solving mathematical equations was formulated in 1904 by mathematician Bjerknes and developed by British mathematician Lewis Fry Richardson. Despite the advancements made by Richardson, it took him working alone several months to produce a widely inaccurate 6-hour forecast for an area near Munich, Germany. Richardson concluded that to predict the weather before it actually happens would involve a room full of people, each computing separate sections of the equations, and a system for transmitting the results as needed from one part of the room to another. Unfortunately, Richardson's estimated number of human calculators needed to keep pace with weather developments was 64,000, all located in one very large room. A great stride in monitoring weather at high altitudes was made in the 1920s with the invention of the radiosonoid. Small lightweight boxes equipped with weather instruments and a radio transmitter are carried high into the atmosphere by hydrogen or helium-filled balloons that ascend to the altitude of about 30 kilometers before bursting. During the ascent, these instruments transmit temperature, moisture, and pressure data back to a ground station. There, the data can be processed and made available for constructing weather maps or insertion into computer models. Today, radiosonoids are launched every 12 hours from hundreds of ground stations all over the world. Mathematician Neumann directed the construction of the computer and put together a team of scientists to apply the computer to weather forecasting. The team determined that impracticality of Richardson's methods could be overcome by using the new computers and a revised set of equations, filtering out the sound and gravity waves in order to simplify the calculations and focus on the phenomena of most importance to predicting the evolution of a continent-scale weather system. In April 1950, the group made a series of successful 24-hour forecasts over North America.
There are 4 basic types of weather forecasting: persistent forecasting, synoptic forecasting, statistical forecasting, and computer forecasting. Persistent forecasting uses what the weather is doing now to predict what it will continue to do. They use satellites, radars, weather balloons, and measuring devices to find what the weather is currently doing. Meteorologists share this information with other meteorologists to show how the weather is changing from place to place. Synoptic forecasting uses basic rules that the atmosphere follows. Meteorologists take their observations and apply those rules to make short-term forecasts. Statistical forecasting uses average temperature, rainfall, and snowfall over the past years to predict what it's supposed to look like at a certain time of the year. Computer forecasting uses their observations of the weather and is put into very complicated equations. These equations are solved by several ultra-high-speed computers to make computer models that give a forecast for the next couple of days. There are different equations and methods that produce different results. Meteorologists must use other methods with the computer to get their best guess on a forecast. This is why different weather stations are different from one another.
For any kind of weather forecast, there are 7 factors which must be considered in order to make an accurate prediction. These factors are temperature, pressure, density, humidity, and 3 components for velocity, 1 being for each direction. More complex systems also utilize the water and ice content in the clouds and the ground. Due to limited computation power, the atmosphere is divided into small sections called parcels. The term primitive equations denotes a computational method that treats the Earth's atmosphere as though it were a fluid on a rotating sphere that utilizes the fundamental laws of thermo and hydrodynamics. For simplicity's sake, the humidity equation is often omitted in the set of primitive equations. The equations of motion are based on Newton's second law and describe the movement of an air parcel. The first equation describes the change of velocity of the parcel in respect to time and has 4 main factors: the pressure gradient force, the Coriolis force, the drag force, and the gravitational force. The second equation shows the pressure gradient force, which is determined by the pressure and density of the atmosphere, as well as the symbol nabla, which is a vector differential operator. Depending on the domain at which it is applied, nabla may be the gradient of a scalar field or the divergence of a vector field. The Coriolis force may be described as the difference between the centrifugal force and gravitation. The rotation of the Earth actually causes the air moving above the planet to be deflected sideways, forcing it to follow a curved path. For the northern hemisphere, air is deflected to the right of its direction of motion, and to the left for the southern hemisphere. In order to determine the wind velocity, there are 3 components that must be used. U is the zonal wind and travels parallel to the circles of latitude. V is the meridional wind and travels parallel to the circles of longitude. For these equations, the latitude is denoted by phi and is within the range of negative pi over 2 to positive pi over 2. Lambda denotes the longitude and uses the same bounds. Z is the distance from the Earth's surface, and R is the radius of the Earth. In many forecasting models, hydrostatic equilibrium is also assumed, meaning that the gravitational and pressure gradient forces are balanced. The equations shown below are the same equations of motion in spherical coordinates. Note that there are only 2 equations in this section. This is because the vertical component of velocity, dw dt, will equal 0. The nabla operator may also be expressed in spherical coordinates, where the e's represent the normalized vectors in each direction. The basic principle underlying the continuity equation is the conservation of mass. If the atmosphere pressure rises in one place, it must also decrease somewhere else, lest you assume that matter was created. Thus, when air moves out of a certain air parcel, it must also find its home in another. In the Eulerian reference frame, this continuity equation may be described as shown. This equation may then be approximated by the third equation, which also filters weak acoustic waves. Similarly to the aforementioned continuity equation, energy must also be conserved between parcels. The movement of thermal energy is a crucial factor in the formation of clouds. In this equation, Cp is the specific heat of air, pressure is constant, and Q dot is the diabatic rate of heat transfer per unit mass. Diabatic simply meaning that heat is transferred.
There are 3 main methods that are used by meteorologists around the world: finite difference method, spectral method, and finite element method. The finite difference method uses a grid structure that divides the Earth's surface into large squares and is layered into the atmosphere. The layers are thinner close to the surface because that's where most of the weather happens. The primitive equations are solved at each grid point, but first they have to be rewritten in finite difference form. They have to define approximations to the derivatives at a specific grid point in terms of finite differences. This is done so the equations can be transformed into a linear equation system. It takes a long time for even supercomputers to solve these equations. A disadvantage of this method is that it does not reveal anything about the behavior of the variables between the individual grid points. The spectral method solves the primitive equations in terms of global functions rather than in terms of approximations at specific points as in the finite difference method. The atmosphere has to be represented in terms of spectral components. The partial differential equations are represented in terms of spherical harmonics. This makes the problem very complex. There is no pole problem when this method is used. At the poles, the solution to differential equations become infinitely differentiable. This simplifies this method. Also, this method can handle finite elements of higher orders than the finite difference method can. This method gives much more accurate results than the finite difference method, but many weather services still use finite difference because it is easier to implement. The final element method is very similar to the spectral method. The dependent variable is defined over the whole domain rather than at the grid points in the finite difference method. But unlike the spectral method, the basis functions are not globally, but only locally non-zero. Also, there are low-order polynomials instead of high-order polynomials. There are many choices for the basis functions, and depending on which functions are used, the finite element method can give very accurate results when applied to irregular grids.
So how does the forecast all come together? Over 210 million observations daily go into the models that meteorologists use. Meteorologists around the country have access to many different models that they can use to make their forecast. Each model outputs many different scenarios. In total, meteorologists have hundreds of possible outcomes that they can choose from. The final forecast is chosen based on many factors, including collaboration with other meteorologists to see what they got in their systems, repetitiveness of the output models, and by looking at the past to predict the future. Accuracy has improved greatly. One-day forecasts are now accurate within about 2.5 degrees. Forecasts will continue to improve with the improvement of the new computers.